We've used definite integrals to find areas. What I want to do now is to see if we can use a definite integral to find an arc length. What do I mean by that? Well, if I start at this point on the graph of a function, and if I were to go to this point right over here, not in a straight line. We know already how to find the distance in a straight line, but instead we want to find the distance along the curve. If we were to lay a string along the curve, what would be this distance right over here? That's what I'm talking about by arc length. By arc length. And we could think about it as, okay, well, that's going to be from x equals a to x equals b along this curve. So how could we do it? Well, the one thing that integration and integral calculus is teaching us is that when we see something that's changing like this, what we can do is we can break it up into infinitely small parts that we can approximate it with things like lines and rectangles, and then we could take the infinite sum of those infinitely small parts. So let me break up my arc length into, infinitely small sections of arc length. So let me call each of those infinitely small sections of my arc length I guess I could say a length differential, an arc length differential. I'll call it ds. ds. And I'm going to draw it much bigger than when at least I conceptualize what a differential is, just so that we can see it. And what do I mean by breaking it up into these ds's? Well, if that's a ds, and then let me do these others in another color, that's another change in infinitely small change in my arc length, another infinitely small change in my arc length. If I summed all of these ds's together, I'm going to get the arc length. The arc length, if I take, is going to be the integral of all of these ds's. All of these ds's summed together over this interval. So we can denote it like this. But this doesn't help me right now. This is in terms of this arc length differential. We know how to do things in terms of dx's and dy's. So let's see if we can re-express this in terms of dx's and dy's. So if we go on a really, really small scale, once again, we can approximate. This is going to be a line. Just the way that we approximated area with rectangles at first. But if you have an infinite number of infinitely small rectangles, you're actually approximating a non-rectangular region, the area of a non-rectangular region. And similarly, we're approximating with lines here, but they're infinitely small and there's an infinite number of them. You are actually finding the length of the curve. But just focusing on this as a line for now. So this distance right over here, I'm just going to try to express it in terms of dx's and dy's. So this distance right over here, that's dx. That's it. You could view this as an infinitely small change in x. And this distance right over here, this is a dy. And once again, I'm being loosey-goosey with differentials, really to give you conceptual understanding, not a rigorous proof, but it'll give you a sense of where the formula for arc length is actually coming from. So based on this, you can see that ds could be expressed as, based on the Pythagorean theorem, as equal to dx squared plus dy squared. Or you could rewrite it as the square root of dx squared plus dy squared. So we can rewrite this. We could say this is the same thing as the integral of, instead of writing ds, I'm going to write it as the square root of dx squared plus dy squared plus dy squared. Once again, this is straight out of the Pythagorean theorem. Now this is starting to get interesting. I've written in terms of dx's and dy's, but they're getting squared. They're under a radical sign. What can I do to simplify this? Or to at least write it in a way that I know how to integrate? Well, I could factor out a dx squared. So let me just rewrite it. This is going to be the same thing as the integral of the square root. I'm going to factor out a dx squared times 1 plus dy over dx squared. Notice this and this is the exact same quantity. If I distribute this dx squared, I'm going to get this right up here. And now I can take the dx squared out of the radical. And so this is going to be the integral of, let me write that in that white color, the integral of 1 plus dy dx squared. And this is interesting because we know what dy dx is. This is the derivative of our function, dy dx squared. And if you take the dx squared out of the radical, the square root of dx squared is just going to be dx. is just going to be dx. Is just going to be dx. Now this is really interesting because we know how to find this between two bounds. We can now take the definite integral from a to b, since now we are integrating a bunch of dx's, or we're integrating with respect to x. We can say, okay, x equals a to x equals b. Let's take the sum of the product of this expression and dx. And this is the formula for arc length. The formula for arc length. And if this looks complicated, in the next video, we'll see that it's actually fairly straightforward to apply, although sometimes the math gets hairy. If you wanted to write it in a slightly different notation, you could write this as equal to the integral from a to b, x equals a to x equals b, of the square root of 1 plus, instead of dy dx, I could write it as f prime of x squared, dx. So if you know the function, if you know what f of x is, take the derivative of it with respect to x squared, add it to 1, take the square root, and then multiply, and then take the definite integral of that with respect to x from a to b. And we'll do that in the next video.